In this example, the limit comparison test is a pretty useful technique. Generally, when you're using the limit comparison test, you want to look at the top and bottom, usually it's a fraction, and you want to look at the top and the bottom of your fraction and look at the most important parts. And so I've got this I squared I to the fourth, so I could compare with the series I equals, well, it wouldn't make sense to start with 0, but we could start with 1 to infinity of I squared over I to the fourth, because that would just cancel to 1 over I squared, and in particular, that's a convergent p-series, because the power is strictly greater than 1. So that's all I have to do when using the limit comparison test, is if often I can just isolate the most important thing on the top and bottom, and if I can compare with that, and if that works, then that will determine the convergence of the overall series. Unless you use a limit comparison test to prove that because the similar series, where I just took the most important things, converges, therefore the original converges. I do that by taking the limit as I goes to infinity. I put the original on the top, and divide by the comparison series terms. So basically I just need to multiply the top by I squared. I flip the bottom, multiply it on the top. That gets me I to the fourth plus I cubed plus 7 over 3I to the fourth plus 2I squared plus 5. And if I factor out I to the fourth on the top and the bottom, cancel, I end up with 1 plus 3 over I. I just realized I made a mistake here. That 7 should have been multiplied by an I squared. So this will be 7 over I squared when I factor out an I to the fourth. On the bottom I get 3 plus 2 over I squared plus 5 over I to the fourth. Now, all these zero out when you take the limit to infinity, so the result is 1/3. And the important thing is that it's between 0 and 1, and infinity, excuse me, between 0 and infinity. It's not equal to 0, it's not diverging to infinity. This is a finite difference. So what does this mean? Basically what this means is that the original series, the one I was asked about, grows at 1/3 the rate of the comparison series. So so what? Well, the idea is that if the comparison series was infinite, 1/3 of infinite is still infinite, so they would both diverge. Here it's convergent. I don't know what this converges to. It actually, this one, you can prove it converges to pi squared over 6, but that's a lot of work. But we do know it converges to something because of the p-series test. So whatever that number is, this series is going to converge to roughly 1/3 of that. The important part is that because this converges to finite, this is 1/3 of finite, therefore it is also finite. Put another way, both series must converge. That's why 0 and infinity don't work, because 0 times infinity is indeterminate. You don't know without more information whether that limit would be finite or infinite. And infinity times 0 would be the same sort of situation. Both series must converge. Last example. Again, don't worry too much about this big number here. It doesn't really matter where you start your series at. That's not going to affect whether the infinite sum is finite or infinite. With the limit comparison test, I can just take the biggest thing on the top and bottom and compare with that. And we'll note that this is a divergent geometric series. It diverges because the ratio 5/4, its absolute value is bigger than 1 or equal to 1. So this should diverge. To prove this, I'll take the limit as n goes to infinity, and I'm going to compare 2 to the n plus 5 to the n over 3 to the n plus 4 to the n. Divide that by 5 to the n over 4 to the n. So I'll flip the bottom. 4 to the n, 2 to the n plus 5 to the n, all over 5 to the n, 3 to the n plus 4 to the n. Multiply these out. Get 8 to the n plus 4 times 5 is 20 to the n, all over. On the bottom we get 15 to the n plus 20 to the n. I'll factor out 20 to the n on the top and the bottom. What I'm left with is 8 over 20 to the n, 15 over 20 to the n, plus 1 and 1. So what was the point of all this? Well, 8 over 20 is a fraction less than 1. Take that to the nth power. That's going to get smaller and smaller and smaller. Eventually it cancels to 0. Same thing with 3/4 to the n. As n goes to infinity, that zeroes out. The result is 1. It's not 0, and it's not infinity. Strictly between. Not equal to. So, what's the point? Well, basically this proves that the series I was asked about and the series I compared with grow at roughly the same rate. The ratio, the difference between these two fractions approaches 1 as a ratio. So since they grow at about the same rate, we know one of them diverges. Therefore, they both have to grow at the same rate. They both diverge. The important thing is that I compared with something that diverges, and when I took the limit of the fraction of the two, I got this number strictly between 0 and infinity. That was enough for me to conclude that my series that I was asked about also diverges.